Hey everybody. In this video, we will be discussing Chapter 10 review, which is on correlation and regression. Okay, so excuse me. So section 10.1, this is on scatter plots and correlation. So very often we're trying in statistics, we're trying to see if one variable influences another. You know, if a raise in this variable shows a raise in another variable. We could, for example, have the following data about two variables. And so they got data from some students. And they wanted to test to see if there's a correlation between the variables hours of study and grade. You know, does the amount of hours that you study show an increase in grade in general? Are the variables related? And so the data we've got here, this student had 6 hours of study. This one had 2. This one has 1. This one has 5, 2, and 3. And this person's grade was 82. This one is 63. This one's 57, 88, 68, and 75. So if we have this data, first of all, we can visualize the data very conveniently in something called a scatter plot. And in a scatter plot, right, we've got our x values and our y values. Essentially, it's just normal plotting points. We just plot these points where our x value is the hours of study, our y value is the grade percentage. And then that'll kind of show us how related they are. The more clumped they are together, the more related they are. The more spread out, the less related that they are in general. So we could plot this on a scatter plot. So we wanted our x value, in this case, our x would be the independent variable, right? We want to see if the grade depends on the hours of study. Usually we'll put that on the bottom axis. So this one would be hours of study. And I'll put here, this is 2, 4, 6, 8, 10. And on the left side, I'll put the grade, which is 0 to 100. So I guess I'll put 100 all the way up here. 0 here. I guess this will be 50, 75, 25. Doesn't need to be exact. And so if I was to plot these as points, here I've got 682, so maybe like around here, 263, something like this, 157, 588, 268, and 375. And in general, we're trying to see if an increase in one gives an increase in another. And what we'll be looking for is what's called a line of regression, which is kind of like a best fit. A best fit line approximation to extrapolate from this data and predict what other values would be likely to happen if the correlation is actually proven to be true. So you could see, since this is like an upward facing slope to the right, and all the values are pretty close to this line, that would mean there is a positive relationship between the variables, which means they're pretty well correlated. We'll discuss what it means to be correlated or not, but basically just first wanted to show an example of a scatter plot. Okay, so I wanted to show a couple examples of scatter plots. So very often we could have something like this. This would be a positive linear relationship. Similar to the example that we just did, the best fit there did show a positive linear relationship. So this is one example of what we can see when seeing if data is correlate or variables are correlated to each other or not. So this means that, an increase in the x value shows on average an increase in the y value, a positive linear relationship. There could also be a negative linear relationship, which means they are still related. It's just that an increase in one shows a decrease in the other. So that would be something along the lines of this. And this would be a negative linear relationship, because as x increases, on average, y decreases. This is called a negative linear relationship. There are other types of relationships that can be discussed, but the other thing I wanted to mention here was things that have no relationship. Maybe it ends up looking like this. In this case, the data looks very, very scattered. There's no rhyme or reason to where they are. It's not like as we increase in x, in general, we increase with y. This means that they have no relationship, or, very little relationship, I guess. And so that's what we're going to be talking about with correlation. Are two variables correlated or not, and how to do that. So I already showed how to, draw a scatter plot here with this example. So again, when drawing a scatter plot, you want the x-axis to be the independent variable. The one that you're trying to see has an influence on the other one. So when drawing a scatter plot, use x-axis for the independent variable. And y for the dependent variable. Right, in the example of hours studied and final grade, we were trying to see if the amount of hours studied influenced your final grade. So the hours of study, that was the independent variable, and the final grade was our dependent variable in that example. Okay, so let me define or talk about correlation a bit more. So statisticians use a measure called the correlation coefficient. To determine the strength of the linear relationship between two variables. And the symbols, the population correlation coefficient is referred to by the Greek letter rho. I know it looks like a P. You could call it P, that's fine. But technically, it's called the symbol rho. And this refers to the population correlation coefficient. It's hard to say. I always get tongue twisted when saying these words. I did pretty good that time, actually. But now that I'm talking, I'm going to probably misspell. Anyway, so rho is the population correlation coefficient. If we were to take the entire population and see how the two variables are related. And usually we're trying to estimate that, which is, what we've done in all of our previous sections, where we try to estimate the population variable, often by using some sample variable. And the sample correlation coefficient in this case is called R. And so what we end up trying to do very often is try to calculate R. And this value of R will tell us how strong or weak the linear relationship is. So what we end up doing is we have this scale right here, and this is about R. So it can have a maximum of 1 and a minimum of -1. And this is like a scale. So on the right, the closer the number, the sample correlation coefficient, aka R, the closer the number is to 1 or -1 means how strong the relationship is. So the closer it is to 1 means the stronger a positive linear relationship is. And negative 1 means a strong negative linear relationship. And a value of 0 means there's no linear relationship. So this is like a scale. The closer it is to the middle, the worse the relationship is, and the closer it is to the edges, the stronger the relationship is. Okay, so again, I want to draw a couple pictures here just to help give you an idea again of this correlation coefficient value. So I'll have something quite highly related. You know, something like this. They're very, very close together. It seems that as x increases, y increases too on average. And if I'm to draw this line of regression, which is what we'll talk about in section 10.2, we see that it's a pretty strong positive linear relationship. You know, this might have an R value of something like 0.9. You know, it would be very close to 1 because they're extremely closely related. Something more spread out would have a value of R closer to 0, maybe an outlier or 2. You know, the line of regression here would be, if I was to guess, I can't even guess at what it is very accurately because the data is so spread out, but it would probably be something like this, I would guess. Something like this. And in this case, our R would be quite small. You know, it's a small, the relation, you know, the line is going up, so it would be closer to the positive linear relationship side, but the values are very far away from the line. So it doesn't quite show a good correlation, and therefore this value would be very low, like 0.1 or something maybe, if I were to guess. And if something is exactly correlated, that means they go exactly on a line. So let me draw the line. Well, I don't want to draw the line first. I'll just try my best. You know, these values are exactly predicted by this line of regression. They are right on it. You know, there's no discrepancy there at all. So this would be like R is equal to 1. This is as strong a linear relationship as you can get. They are right on the line. So this value of R, again, is essentially telling us how related these are. And the closer the values are to this line of regression that we can draw to kind of average the values in a way, the closer the value is to 1 or negative 1. Let's do a negative R example. Something like this. This would probably have an R of something like negative 0.7. You know, the slope is negative, and the values are kind of close to the line, not like really, really close, but not really, really far. So maybe something like negative 0.7 or something like that. Just trying to, you know, give some very general examples here just to get a little bit of practice on what R means, what it looks like on the scatter plot. So calculating this value of R with the X and Y values given to us is from a formula. It's not a nice formula. I've got to say, it is a very ugly formula. Not easy to memorize for sure. When I give this to my class in person on the test, I give them this formula because it's a lot to memorize. Okay, so here's the formula for R. I hate the book's notation, so let me pause while I write it here because I want to double, triple check everything to make sure I get it right. Because there's a lot of little, like, if I get one symbol wrong or one parenthesis wrong, it could be something completely different. So just give me a sec here. Okay, so here's our value, or rather our formula for R. Not nice. Pretty nightmarish of a formula. Our numerator is n. Remember, n is the number of data values in the sample. I guess I could write all this. Oh, not really. Anyway, then we've got n times the sum of all the xy's. So we take the product. We do x times y for every data value, and then we add all those up. That's going to be that value. Minus the sum of all the x's times the sum of all the y's. And then all over the square root of, and then there's these two products here. The first bracket, n times the sum of all the x squareds, minus the sum of all the x's squared. And then the right bracket, we've got n times the sum of all y squareds, minus the sum of all the y's squared. And then you multiply those together, take the square root of them, that's the denominator. I know, it's a very, very awful formula. We'll do some examples to try to compartmentalize all the data in a more digestible, understandable way. So let's go ahead and look at some examples of calculating this correlation coefficient. I guess we could do it for the example that we just had. Sure, why not? Let's use this data and calculate R for this one. Okay, so we've got our X column, we've got our Y column. What other columns are we going to need? We pretty much need all the summations. You want to get a column for everything that you're going to need to sum up. So we need a column of X times Y as well. We've already got a column for the sum of all the X's. That's just going to be down here. We've already got a column for the sum of all Y's. That's just going to be right here. So I guess that's actually all the columns we need, isn't it? Well, I guess we also should put in x squared because this one right here. And a column for y squared as well because of this one right here. So we want a column of x squared and a column of the y squared values. And you could do every question this way. You can have it be the same columns every single time. Right? We need xy, x squared, and y squared for these summation values. This one here, and this one here. The other summations are going to be covered by these two boxes right here at the end, right? I could calculate the sum of all the x's and the sum of all the y's right now. This is 8, 9, 14, 16, 19. Also, our n here, the number of data values, essentially the number of rows that we have, n is, in this case, 6. And the sum of all the y's, I guess I'll get the calculator up for this one. 82 plus 63 plus 57, 88, 68, and 75. 433. Okay, and so we've just got to do the work for the other columns, right? In the next column, we just do whatever's in x times whatever's in y, and that will be x times y. So first, for this first one, we do 6 times 82. It's 492. 2 times 63. I could do this in my head, but I don't want to make a mistake, so I'm just going to put everything in the calculator. Well, 1 times 57, that's just 57. 5 times 88, 440. 2 times 68, 136. 3 times 75, 225. In the next column, we do x squared. Whatever's in the x column, we square it. So this one's 6 squared, that's 36. 2 squared, that's 4. 1 squared, that's 1. 5 squared, that's 25. 2 squared, that's 4. 3 squared, that's 9. And then the y squareds, definitely need the calculator for this one. 82 squared is 6724. 63 squared, 3969. 57 squared, 3249. 88 squared, 7744. That's a bit of a weird number. I didn't expect that. 68 squared, 4624. And 75 squared, 5625. And now we could get all these summations. So for the sum of all the xy's, I do 492 plus 126 plus 57 plus 440 plus 136 plus 225. This gives me 1476. So again, this is all the sum of all the x's. This one's the sum of all the y's. This one's the sum of all the xy's. The sum of all the x squareds, 36 plus 4 plus 1 plus 25 plus 4 plus 9, that's 79. And the last one, these numbers are a bit of a pain. 6724 plus 3969. Just be really careful when doing this stuff. Right, one wrong button and it's gonna be wrong. $31,935. And this is the sum of all the y squareds. So when doing these questions, when calculating R, the correlation coefficient, you always want to do this. Make this chart. You've got a column for X, a column for Y. That's what you're given. That's the data, the X and Y column. You're given that. And then we have to make a column for XY, a column for X squared, a column for Y squared. And then we could find the summations of all of those. And then we can plug all of these into our formula for R. rather than do all those calculations on the fly. Do them all ahead of time so that when we're calculating R, it's all that much easier. So we've got our formula for R here. So what are we going to get? Again, remember, n is 6 in this case. There's 6 data values. So we get 6 times the sum of all the xy's. It's 1476. And then minus the sum of all the x's. That's 19. The sum of all times the sum of all the y's. It's 433. All over the square root of. So for bracket n, which remember is still 6, times the sum of all the x squareds. That's 79. Minus the sum of all the x's, which is 19, squared. So that's just 19 squared in the first bracket. And the second bracket, it will be, that looks like a point. Let me just fix that. It'll be 6 times the sum of all the y squared. So that's 31,935 minus the sum of all the y's, which is 433, squared. Okay, so I know it's definitely a pain, big, huge calculation here. But all of this is compartmentalized now pretty well. We just got to plug and chug. So 6 times 1476, this is 8856, minus, okay, what's 19 times 433? It's 8227. This is all over the square root of, so this, let me calculate the whole first bracket. 6 times 79 is 474. Well, never mind. I'll just do that. 6 times 79, that's 474, minus 19 squared, which is 361. Close bracket, open bracket. 6 times 31,935. It's 191,610 minus 433 squared, which is 187,489. We're getting there. So the numerator, 8856 minus 8227, that's 629, over the square root of, what's this first bracket? 474 minus 361, 113, and times the second bracket, 191,610 minus 187,489 is 4121. Almost there. So it's really 629 over the square root of 113 times 4121, which is 465, 673. I guess at this point I can just plug this in and see what we get. So 629 over the square root of 465,673. We're going to get 0.9217. And so, on our scale of correlation of -1 to 1, this is pretty high up there, right? Our R in this case would be around here. And what we're going to use to determine whether something is correlated or not, we're gonna make our dividing value of 0.75 tell us that or not. So if our R is between 0.75 and 1, that means there is a high linear relationship. Anything in this range, essentially, has a high positive linear relationship. So something like 0.6 is not going to be a high positive linear relationship. It'll just be like a medium linear relationship or something like that. But we'll consider something higher than 0.75, but less than or equal to 1, to have a high linear relationship. So in this case, we get a high linear relationship. High positive one, in fact. And of course, anything between -1 and -0.75 is going to have a high negative linear relationship. That's like what we're going to use as the cutoff, essentially. Different books use different values for cutoffs, so I'm just making sure we make it concrete for this class. Okay, so this value of r, pretty tough to calculate, very, very tough to calculate. It's a very complex formula. The hardest one we've seen in this class, for sure. So really just try to compartmentalize all of the data into tables so that you could plug it into the formula and start doing the calculations one by one. Like if you have a graphing calculator, you could put it in at this point, but not everybody will have a graphing calculator. So if you don't, you got to break it into smaller pieces like this. Okay, so I hope that example makes sense. We could do another one. Let me just get some data. Okay, so I've got this question here. It says a researcher wishes to see if there is a relationship between the number of reported cases of measles and mumps for a recent 5-year period. Is there a linear relationship between the two variables? So if you just look at the data here for a minute, in the first column it says 43 measles cases, 800 mumps cases. Then we've got 140 measles cases, 454 mumps cases. So the measles cases went up, but the mumps cases went down. Again, when we go to 71 measles cases, there's way more, this time way more mumps cases. And then at 63, there's way more mumps cases. And then at 212, it spikes down to 370. So to me, it doesn't look like they're very related. So I would expect to see a value of r very close to 0 somehow. So, this is our x, this is our y. Let me just structure it as a table as we had before. Okay, so 43, 800, 140, 454, 71, 1991, 63, 2612, 212, 370. That's our x and y data. And so remember, for our formula, we need a column for x, y. And the numbers are going to be big here. It's going to have to be a pretty big column. A column for x squared and a column for y squared. And then we'll have the summations at the bottom, which we'll use to plug into the formula for r. So let's go ahead and calculate all this. 43 times 800, 34,400. 140 times 454, 63560. I think you might be able to have a spreadsheet at this point. They probably let you export the data to a spreadsheet. And so you could just make a column for x, y, have it do the product of the first and second columns, make a column for x squared, have it do, the first column squared, and then a column for y squared, have it do the second column squared. And then it'll do all that stuff really quickly. Whereas here I'm doing it manually, of course it's going to take a lot longer, more room for error as well. 141, 361. And we've got 63 times 2612, 164556, and 212 times 370. Oh, jeez, I just realized I had it off the screen, sorry. 78,440. A column for x squared, so I'll do 43 squared. 140 squared. It's 1849. 19,600. We need 71 squared, 63 squared, 5041, 3969, 212 squared, 44944. And a column for the y squareds as well, so 800 squared, 640,000. 454 squared, 206,116. Yeesh. 3964. 081. 'kay, finally got all those. Now we just need to sum every column. This will give us the sum of the x's, the sum of the y's, the sum of the xy's, the sum of the x squareds, the sum of the y squareds. $529 for the first one. I really probably should have just done this in Excel because this is a lot of room for error here. These numbers are pretty big. Yeah. I also don't have you guys here right now to back me up, see if I do anything wrong while I'm doing it. So I'm trying to double, triple check to make sure I'm not inputting anything wrong here. I hope I haven't messed up. Let's see, 482317. Okay, pretty big values here. Hope this one doesn't break the calculator. Okay, here's our formula for the correlation coefficient. Just plug everything in. What's n in this case? In this case, n is 5. There's 5 data values. It's the number of columns that we've got right here, or the number of rows that we've got right here, essentially. Right, this is 1 data value, 2 data values, 3 data values, 4 data values, 5 data values. So our n is 5. So what do we get here? 5 times the sum of all the xy's, that's the 4, 8, 2, 3, 1, 7 number, minus the sum of all the x's, that's 529, times the sum of all the y's, that's 6227. And all over the square root of, this is 5 times sum of the x squareds, that's 75,403, minus the sum of all the x's, which is 529 squared. And then the other one will have 5 times the sum of the y squareds, which is 11,769,641. And then minus the sum of all the y's squared, which is 6,227 squared. So I'm just going to plug this whole thing in my calculator and get the value. I showed you guys earlier how to do it in pieces if you don't have a graphing calculator like this, but I'm just going to do the whole thing in my graphing calculator here. So I'm going to do numerator first in a big parentheses. So 5 times 482,317 minus 529 times 6227 divided by, nope, wrong button, divided by, and then the denominator is a square root, and the first term I'll put in parentheses. So we've got 5 times 75403 minus 529 squared, right? That's that first bracket, essentially. And then the second bracket, I'll start another parenthesis. 5 times 11769,641. Oops, I forgot the square up here on the 6227. Minus 6227 squared. Enter. So it seems here we get approximately negative 0.6319. And so they're really not very closely related. It would be, I guess, a weak linear I'll just say a weak linear, or a weak negative linear relationship is what I wanted to say. Because it's not quite close to -1. It's not quite close to 0 either, so there might be some relationship there. But definitely not strongly related in any way. So that's a pretty good example with pretty horrible numbers, of course. I guess we could do one. I'll show you guys one in Excel because that's I would really encourage you guys to do that if it allows you to do so. Okay, so I got another example here. It says school administrators wondered whether class size and grade achievement in percent were related. A random sample of classes revealed the following data. Are the variables linear related? So, we had if it was a 15 student class, the average grade was 85. There was a 10-person class, the average grade was 90. An 8-person class, the average grade was 82, etc., etc. And so they want to see if there's a positive or negative linear relationship stating that, either as we increase the number of students, does the grade go up or does the grade go down? Or is there no relationship at all? So let's pull up Excel. Google Sheets, of course, is free. And I know in the software, the Alex software, it allows you to just copy and paste the data over. So let me do that here. 1510 8 2018 6. This is our X column. And then we've got 85, 90, 82, 80, 84, 92. That's our Y column. I'll even label them here. This is X, this is Y. Oops. And so we want a column for X, Y, X squared, and Y squared. So you just hit an equal sign. When you want to do a formula in Excel or Google Sheets or something like that, you hit the equal sign. That's very important. That's what starts formula calculation. Equal sign first. And so we want to do whatever's in the first box times whatever's in the second box, and then we could copy and paste that down. So I just click this box where the 15 is in that second row. Then I hit times. Then I click the box with the 85, and then I enter. And it even gives a suggested autofill, doing the same thing in each row. Sure, why not? Or you could just, of course, copy, paste. I could just copy this and then paste. And for x squared, right, we hit the equal sign, and we want to square whatever's in this entry. So I click this box, I do up arrow 2 to represent squaring something, and then I enter. So let me just copy this, highlight these, control paste, or paste. Same thing for the Y column, hit the equal sign, I hit this box, I want to square whatever's here. Okay, so we've got our columns that we need. Now we just need to come up with the summation. Let me color this row a little bit different. So we just sum up all of these. So in order to do this, we hit the equal sign, and we type in sum, and then we can highlight the values we want to sum up. So sum and then parenthesis, and then I'll just highlight all these, and then I close the parenthesis, and I hit enter. And that gives me the sum of that column. So same thing for this one. Sum. So a little mini Excel lesson here. Hope this helps. So we've got all our summations. This one's the summation of x. This is summation of all the y's. This is summation of all the xy's. This is summation of all the x squareds. This is summation of all the y squareds. So let me put a little box here for r, and I'll do the formula for r. Very complex one, a formula, remember. Let me pull it up here on my other screen so I have it. Okay, so remember, what's n in this case? Let me put a box for n as well. There's 1, 2, 3, 4, 5, 6 data values. I'll put that here. So here I'll put r. This is exactly what we're looking for, so I'll put this in like a green color. This is kind of like the culmination of all the data, which shows us the correlation, right? So the formula here, okay, parenthesis. So it's this could be tough. Okay, well, this is n times, and I want the sum of all the xy's. That's this one. And then minus the sum of all the x's times the sum of all the y's. Parenthesis, and then division. Okay, there's my numerator, and then division. We want the square root, so that's sqrt parenthesis. So the square root of, and so bracket, right? The first bracket, I'll put up another parenthesis to represent that, and then n, which is this, times the sum of all the x squareds, that's this, minus the sum of all the x's, that's this, squared, parenthesis times parenthesis, and then n times the sum of all the y squared, so that's this, minus the sum of all the y's squared, and then I got to close the square root off. Bam. So hope this works. I'm pretty sure I did it right. No. Oh no. What'd I do? What did it say there? I probably should have read the error. Function multiply parameter to expects number values. Oh, I hit the wrong box. I didn't hit the number in one of these. It should be everything in the eighth. B12. Oh yeah. It should be. These should all be in the eighth column. I kept hitting the. I hit the text instead of the number for these. Sorry. I need to change all these to the eighth row. In another lifetime, I was a computer programmer. I did a lot of Excel work, so I'm really good with this. Promise. Okay, so we end up getting our correlation coefficient here, negative 0.6731 approximately. So I want to show you guys how to do that on Excel. You know, you really want to use Excel for these probably, especially when the numbers are as insanely as big as this. It's very likely you can make an error. Like, no matter how good you feel like you are at this, how confident you are, everyone's only human. Everybody makes mistakes, and with this, you know, with all of these numbers, all these huge numbers, the room for error grows. So, especially when the numbers are really big, I would highly encourage you to get used to using Excel. It's an extraordinarily useful tool to start learning how to use. Okay, so that covers section 10.1. Let's talk about 10.2. Okay, so section 10.2. Here we're talking about regression, which is that line that I was talking about through the data, through the scatter plot. Essentially, we'll be finding that line, the equation of that line here in this section. So the formula for the line of regression is the following. Y is equal to ax plus b. And a and b are pretty ugly. The value for a is n times the sum of the xy's minus the sum of the x's times the sum of the y's over n times the sum of the x squareds minus the sum of the x's squared. That's the value for a in y equals ax plus b. And b is the sum of the y's times the sum of the x squareds minus the sum of the x's times the sum of the xy's all over n times the sum of the x squareds minus the sum of the x's squared. Let me just pause for a second, make sure I got it right. Yep, looks right. Okay, and so this is how we find, again, let me go back like here. If we wanted to actually find the equation of these lines that I've got in orange, it is given to us by this equation right here. This is the equation for the line of regression. So let's go ahead and do some examples to actually find the line. We could bring up data that we had earlier where we've already calculated all of those values. How about this one? So we saw that what was the correlation here? It was pretty high correlation. So when we plot this data and plot the line, the data is going to be very close to the line. So let's look at an example here of calculating the line of regression for the first example that we looked at. Okay, so here's our formula. We've already got all these summation values that we need. So let's figure out what A and B are. Okay, so for A, we get 6 times 1476 minus 19 times 433 over 6 times 79 minus 19 squared. We just get the numerator and denominator. Because the denominator is the same in both, so you don't really have to calculate it twice, I guess. So the numerator is 6 times 1476 minus 19 times 433. Oops, I put 466. 629 over the denominator, which is 6 times 79 minus 19 squared, which is 113. Oops. And 629 divided by 113 is approximately, let's go 3 decimals, 5.566. There's our value for A, or you could just leave it as 629 over 113 or whatever this reduces to. What's it reduce to? Nothing. It's actually simplified already. But that's our A value for y equals ax plus b. Essentially, it's our slope, right? It's the slope there of our line. And the one over here on the right, this is essentially our y-intercept, right, of the line. And so let's see what we get here. Again, our denominator is 113. We already calculated that. It's the same denominator in each formula. The numerator, though, we'll get here 433 times 79 minus 19 times 1476. Okay, what's the numerator? 433 times 79 minus 19 times 1476. 6163. So what's that divided by 113? Approximately 54.54. So our line of regression, our final answer that we were looking for, is y is equal to 5.566x plus 54.54. That would be our line of regression for this data. I'm going to go ahead and plot it on Desmos, plot all this stuff on Desmos. Just give me a sec. Okay, so here I plotted all the points and I scaled it accordingly. You know, my x-axis, I only allowed 0 to 10 because the x values didn't go vary very much. You know, there are only values between 0 and 10. The y values, I guess from 0 to 100 would be a little bit better. So there's our data, you know, there's our scatter plot. So our line should be, you know, something close to this, if I was to guess. And the line that we found is 5.566x plus 54.54. There we go. And so there would be our line of regression. And kind of, you know, like we could extrapolate in the future. So if we wanted to say, you know, what grade would you get if you studied 8 hours? Well, you could expect to get a 99, you know, according to this. Of course, it's not perfectly accurate, but, you know, in general, it tends to go this way. As you study more hours, in general, you know, not always, but in general, you end up doing better on average. Okay, and that's regression. This is how we find our line of regression with this A and B value. So let's get a little bit more practice. But this is pretty much all I wanted to talk about in this section. It's all just finding lines of regressions. So I guess we could do a couple more examples. Might as well do some that we already have the data for. How about this measles and mumps one? Let's find the line of regression here. I know these formulas are definitely a pain, but you don't have to memorize them. You just have to know how to apply them. And I'm trying to show a bunch of examples here just to give you guys enough resources, essentially, to fall back on when you're trying these yourself. So again, here we need to calculate our A and B for the formula y equals ax plus b. And we've got all of our data, all the summations that we need here already. And in this case, n was 5. So we'll get here 5 times 482,317 minus 529 times 6227 all over 5 times 75403 minus 529 squared. Let me just do the numerator first. 5 times 482,317 minus 529 times 6227. It's negative 882,498. And our denominator, 5 times 75403 minus 529 squared, 97174. Remember that denominator is the same in both, so I already know this is 5 times 75403 minus 529 squared, which is 97174. The numerator is different though. The sum of the y's, that's 6227, times the sum of the x squareds, 75403, minus the sum of the x's, that's 529, times the sum of the xy's, which is 482317. Thank goodness we don't need the y squareds, because that's the 11 million number. So what do we get here? I'm just going to plug the whole thing in the calculator, the whole numerator, that is. 6227 times 75403 minus 529 times 482317. 214388. So let me approximate these values to 3 decimals, or 2 decimals, I guess, 2 or 3. Negative 882498 divided by 97174, approximately negative 9.082. And the b value, 214,388,788 divided by 97174. Approximately 2206 point what? 236. So our line of best fit would be y is equal to negative 9.082 plus 2206.236. I just want to go ahead and plot this on Desmos to make sure it's right, essentially. If I see it doesn't line up rightly, I know I probably made some error. It won't let me. Okay. So let me plot all the points again. 43,800. 140, 454. 71, 1991. Good year. 63, 2612. And 212370. Let me try to scale it properly, because obviously we can't see anything right now because it's not scaled properly. The x values are between 0 and 200. 212 is the highest one, actually, so maybe I should go like 0 to 300 in the x values. And for the y values, the lowest is 454, the highest is 2612. Let's do like 0 to 3000. Then we should end up seeing the points. Yeah, there they are. 1, 2, 3, 4, 5, right? That was our n. Yep, 5. These don't look very correlated to me, guys. Remember, what was our r here? Negative 0.6319. It was a very bad correlation, a very weak correlation. And now that we see the scatter plot of these, we definitely know that our line of best fit here, our line of regression, is not going to be a very good approximation. Negative 9.082x. I forgot the x there. Sorry. There it is. There would be our line of regression, and you could see the points are almost all really far away from it, except this one over here. And so it really doesn't approximate the data very well at all. And we kind of see that manifested here with this line of regression. It does match with this value of r, which was a weak negative linear relationship. Remember, we look at the scale to see how linear related they are, or how linked up together they are, essentially. And that was an example where we found that they shouldn't have been very linked together, and we do see that here in the data. Okay, so that's pretty much all I wanted to talk about in this section, and that will actually conclude Chapter 10. So thank you for watching the video. This is actually the last material for class, the last new material. So after this, there will be a third test, and that will be it. So good luck on the Chapter 10 homework and the Chapter 10 quiz. Of course, always feel free to email me if you have any questions, comments, concerns, anything like that. And other than that, thank you for watching. Have a great rest of your day.